The James Webb Space Telescope has just peered deeper into the cosmic past than ever before, and what it found shouldn't exist. A galaxy so ancient, so impossibly massive, that it challenges everything we thought we knew about the birth of our universe. This discovery isn't just rewriting textbooks, it's forcing us to question whether our most fundamental understanding of reality itself might be incomplete. Welcome to another journey into the mysteries that shape our existence. I'm here to guide you through one of the most profound discoveries of our time, a finding that sits at the very edge of what science can explain. Tonight, we'll explore how a single observation from the depths of space is quietly revolutionizing our understanding of time, matter, and the very fabric of reality. So settle in, take a deep breath, and prepare to have your perspective on the universe gently transformed. Imagine, if you will, standing at the edge of time itself. You're holding the most powerful telescope humanity has ever created, peering back through billions of years of cosmic history, watching the universe unfold in reverse. You expect to see smaller, simpler structures as you look further back, like watching a movie of construction played backwards. Instead, you discover something that shouldn't be there at all. This is precisely what happened when astronomers turned the James Webb Space Telescope toward a seemingly empty patch of sky and found JD's GS 14-0, a galaxy that existed just 290 million years after the Big Bang. To put this in perspective, if the entire history of the universe were compressed into a single year, this galaxy would have formed in early January, when the cosmic calendar had barely begun. But here's where things become truly extraordinary. This ancient galaxy isn't the small primitive structure we would expect from such early times. Instead, it's massive, bright, and surprisingly mature, stretching over 1,600 light-years across and containing hundreds of millions of times the mass of our Sun. It's as if you discovered a fully grown oak tree in what should have been a field of seedlings. The implications ripple outward like stones thrown into still water. According to our current understanding of physics, there simply wasn't enough time for such a massive galaxy to form so early in the universe's history. Stars need time to be born, live their lives, and create the heavy elements necessary for galaxy formation. Gravity needs time to pull matter together into such large structures. Yet here it is, shining across the cosmic dark, a testament to processes we don't yet understand. As you contemplate this mystery, notice how it mirrors the questions we ask about our own existence. How do complex patterns emerge from apparent chaos? How does order arise from disorder? These aren't just cosmological questions. They're deeply personal ones that touch the very core of what it means to exist in an apparently ordered universe. To truly appreciate the magnitude of this discovery, we need to understand the cosmic timeline itself. The Big Bang, that moment of ultimate beginning, occurred approximately 13.8 billion years ago. But this wasn't an explosion in space, as many imagine. Rather, it was the expansion of space itself, a stretching of the very fabric of reality that continues to this day. In those first moments, the universe was unimaginably hot and dense. There were no atoms, no stars, no galaxies, just a seething ocean of energy and fundamental particles. As space expanded and cooled, the first atoms formed, primarily hydrogen and helium, in an event we call recombination. This happened about 380,000 years after the Big Bang, and it marked the moment when the universe became transparent for the first time. The cosmic microwave background radiation that we detect today is the afterglow of this moment, a faint whisper of light that has been travelling through space for over 13 billion years. It represents the earliest light we can observe, the fundamental limit of our ability to see into the past. Beyond this cosmic horizon, the universe remains forever hidden from our view. But between that moment of transparency and the formation of the first galaxies, there existed what astronomers poetically call the cosmic dark ages. This was a time when the universe was filled with neutral hydrogen gas, but no stars had yet formed to illuminate the cosmic darkness. The first stars, massive and short-lived, began to form perhaps 100 to 200 million years after the Big Bang, ending this period of darkness and beginning what we call cosmic dawn. This is where our impossible galaxy becomes truly remarkable. JDES-GS Z14-0 formed during this cosmic dawn at a time when the universe was still emerging from its dark age. Yet instead of being a simple collection of first-generation stars, it displays the complexity and maturity we would expect from much later epochs. Take a moment to reflect on this timeline. The galaxy we're discussing formed when the universe was less than 3% of its current age. If you think of your own life, this would be like discovering that you had developed complex philosophical thoughts before you could walk or even speak. The analogy isn't perfect, but it captures something of the profound mystery we're confronting. The James Webb Space Telescope itself is a marvel that deserves our contemplation. Orbiting the Sun at a distance 4 times farther than the Moon, it sits at what's called the second Lagrange point, where the gravitational forces of Earth and Sun balance perfectly. Here in the cold depths of space, its massive mirror collects the faint infrared light that has been travelling since the universe's youth. This telescope doesn't just see farther than its predecessors, it sees differently. While the Hubble Space Telescope primarily observes invisible light, Webb specialises in infrared radiation. This is crucial because as the universe expands, the light from distant galaxies gets stretched to longer, redder wavelengths. The most ancient light, by the time it reaches us, has been stretched all the way into the infrared spectrum. When astronomers first pointed Webb toward the constellation Lynx and began their deep field observations, they expected to find some early galaxies, but they didn't expect to find galaxies quite this early, quite this massive, or quite this mature. The discovery of JD's GS Z14-0 was, in the words of the researchers themselves, a cosmic miracle. The galaxy's properties continue to surprise. Its light suggests it contains relatively little dust, which means we can see its stellar populations clearly. The stars appear to be young and actively forming, yet the galaxy itself must have assembled remarkably quickly to reach such a massive state so early in cosmic history. It's as if nature found a fast track to galaxy formation that our current theories don't account for. Recent observations have added another layer to this mystery. Astronomers have detected oxygen in this ancient galaxy, marking the most distant observation of this element ever made. The presence of oxygen tells us that multiple generations of stars had already lived and died, creating heavy elements through nuclear fusion and distributing them through stellar explosions. This process of stellar alchemy should have taken much longer than the 290 million years available. As you process these discoveries, you might feel a sense of vertigo, a recognition that our place in the cosmic story is more mysterious than we previously imagined. This feeling isn't uncomfortable if we let ourselves rest in the wonder of it. We are part of a universe that continues to surprise us, that holds secrets we're only beginning to glimpse. The discovery of JDES GSZ 14-0 doesn't break the laws of physics in any literal sense. The universe isn't suddenly behaving chaotically or violating fundamental principles. Rather, this galaxy is revealing that our current models of cosmic evolution are incomplete, like a map that accurately shows the major highways but misses some important backroads. Our standard model of cosmology, known as lambda CDM, has been remarkably successful at explaining the large-scale structure and evolution of the universe. It incorporates dark matter, dark energy, and the cosmic microwave background radiation in a framework that has made numerous successful predictions. But the early formation of massive galaxies like JDS-GSZ 14-0 suggests that something is missing from this picture. One possibility is that the early universe was more efficient at forming stars and galaxies than we previously thought. Perhaps the first stars were different from what we observe today, burning brighter and living shorter lives, rapidly enriching their environments with heavy elements. Or perhaps dark matter, that mysterious substance that makes up most of the matter in the universe, clumped together more quickly in the early cosmos than our simulations suggest. Another intriguing possibility involves the nature of cosmic inflation, that period of exponential expansion thought to have occurred in the first fraction of a second after the Big Bang. Some models suggest that inflation could have created conditions that allowed massive structures to form more rapidly than standard theories predict. The seeds of galaxy formation might have been planted earlier and grow more quickly than we imagined. These aren't revolutionary overturns of physics, but rather refinements of our understanding, like adjusting the focus on a microscope to see details that were previously blurred. Science progresses through such discoveries, moments when observations push us to expand our theoretical frameworks to accommodate new realities. Consider how this process mirrors the growth of understanding in your own life. Often a single experience or insight can reshape your entire perspective, not by destroying what you previously knew, but by placing it in a larger, more nuanced context. The universe, it seems, operates in much the same way, constantly revealing new layers of complexity and beauty. As we delve deeper into this mystery, we begin to see how the discovery of JD's GSZ 14-0 connects to broader questions about the nature of existence itself. The galaxy didn't form in isolation, but emerged from the cosmic web, that vast network of dark matter filaments that provides the scaffolding for all large-scale structure in the universe. In the early universe, tiny quantum fluctuations, stretched to cosmic scales by inflation, provided the seeds from which all structure would eventually grow. These fluctuations were incredibly small, differences in density of less than 1 part in 100,000. Yet over hundreds of millions of years, gravity amplified these tiny variations into the galaxies, stars, and planets we see today. The fact that massive galaxies could form so early suggests that these primordial fluctuations might have been stronger than we thought, or that the processes of structure formation were more efficient than our current models predict. It's possible that the early universe was a more dynamic, rapidly evolving place than we previously imagined. This discovery also highlights the interconnected nature of cosmic evolution. The formation of the first galaxies wasn't just about gravity pulling matter together. It involved the physics of star formation, the chemistry of element creation, the dynamics of gas flows, and the mysterious influences of dark matter and dark energy. Each of these processes influenced the others in ways we're still trying to understand. The oxygen detected in JADES-GSZ 14-0 tells a particularly compelling story. This element was forged in the nuclear furnaces of massive stars and distributed through space when those stars exploded as supernovas. The presence of oxygen in such an early galaxy means that stellar birth, life, and death cycles were already well underway when the universe was still in its infancy. Take a breath and imagine the profound beauty of this process. Every atom of oxygen in your body was once inside a star that lived billions of years ago. You are literally made of stardust, connected to the cosmic story in the most intimate possible way. The discovery of ancient oxygen in distant galaxies isn't just an abstract scientific finding, it's a reminder of your deep kinship with the cosmos itself. As we sit with these discoveries, new questions naturally arise, each one opening pathways to even deeper mysteries. If massive galaxies could form so early in the universe's history, what does this tell us about the nature of time itself? How do we reconcile the rapid formation of complex structures with our understanding of cosmic evolution? Some researchers have suggested that our concept of cosmic time might need refinement. Perhaps the early universe evolved more rapidly than we thought, with processes that normally take billions of years compressed into hundreds of millions. This wouldn't violate the laws of physics, but would suggest that the early cosmos operated under conditions very different from what we observe today. Others propose that dark matter, that invisible substance that comprises most of the matter in the universe, might have properties we don't yet understand. Perhaps it clumped together more efficiently in the early universe, providing the gravitational scaffolding for rapid galaxy formation. Or perhaps dark energy, the force driving cosmic acceleration, behaved differently in the universe's youth. These possibilities remind us that our understanding of the cosmos is still evolving. The universe continues to surprise us, revealing new layers of complexity and beauty with each technological advance. The James Webb Space Telescope has been operational for only a few years, and already it's reshaping our understanding of cosmic history. As you contemplate these mysteries, notice how they reflect the ongoing process of discovery in your own life. Just as the universe reveals its secrets gradually, your understanding of yourself and your place in existence continues to deepen with time and experience. Each new insight builds upon previous knowledge while opening doorways to even greater mysteries. The discovery of JADES GSZ 14-0 is just the beginning of what promises to be a revolution in our understanding of the early universe. As Webb continues its observations and as new telescopes come online, we can expect more surprises, more questions, and more opportunities to marvel at the extraordinary complexity and beauty of the cosmos we inhabit. As we drift deeper into this cosmic mystery, something remarkable begins to emerge from the data. The light reaching us from JADES GSZ 14-0 has been travelling for over 13 billion years, carrying with it the signature of processes that occurred when the universe was still learning how to make galaxies. This ancient light doesn't just tell us about distance and time, it whispers secrets about the fundamental nature of cosmic evolution itself. When astronomers analyze this primordial light, they discover something unexpected in its spectrum. The galaxy appears to be forming stars at a rate that should have exhausted its gas supply long before it could grow so large. Yet there it is, blazing across the cosmic dark with an intensity that suggests abundant fuel for continued star formation. It's as if the early universe had access to resources and processes that operated by different rules than what we observe today. The colours of this distant light reveal another puzzle. JADES GSZ 14-0 appears surprisingly blue in the ultraviolet spectrum, indicating the presence of young, hot stars. But blue light from such massive young stars should be accompanied by specific signatures of stellar feedback, winds and explosions that regulate star formation. Instead, the galaxy seems to be forming stars with remarkable efficiency, as if the normal processes that limit stellar birth were somehow suppressed or operating differently. Take a moment to consider what this might mean. You're looking at light that began its journey when the universe was younger than a typical human lifespan. The photons striking the Webb telescope's mirrors today were emitted by stars that lived and died before our galaxy had fully formed, before the heavy elements that make planets possible were widely distributed through space. Yet these ancient stars were already organized into a structure more massive and complex than many galaxies we see in the modern universe. This discovery challenges our understanding of what astronomers call the galaxy mass function, essentially a census of how many galaxies of different sizes should exist at different epochs in cosmic history. According to our current models, massive galaxies like JDES GSC 14-0 should be extremely rare in the early universe. The probability of finding such a galaxy so early should be vanishingly small, yet here it is, captured in exquisite detail by humanity's most advanced telescope. Behind every cosmic discovery lies mathematics, those elegant equations that describe how matter and energy behave across the vastness of space and time. The detection of JDES GSC 14-0 forces us to examine the mathematical models we use to understand galaxy formation, and what we find is both humbling and inspiring. The process of galaxy formation involves a delicate interplay between gravity, which pulls matter together, and various feedback mechanisms that can halt or regulate star formation. When massive stars explode as supernovas, they inject energy into their surroundings, heating gas and potentially driving it out of the galaxy entirely. This stellar feedback is thought to be crucial in determining how quickly galaxies can grow and how massive they can become. But the properties of JDES GSC 14-0 suggest that either stellar feedback was less efficient in the early universe, or that other processes were at work that we don't yet fully understand. Perhaps the dark matter halos that provide the gravitational scaffolding for galaxy formation were denser or more concentrated in the early cosmos, or perhaps the gas falling into these early galaxies was colder and denser, allowing stars to form more efficiently. Some theoretical models propose that the first galaxies formed in rare, highly overdense regions of the early universe, cosmic peaks where matter was concentrated far above the average density. These special locations might have acted as nurseries for rapid galaxy formation, allowing massive structures to assemble in timeframes that would be impossible under typical conditions. As you contemplate these mathematical possibilities, notice how they mirror patterns in your own experience. Complex systems, whether cosmic or personal, often emerge through the interplay of competing forces. Growth and regulation, expansion and constraint, creation and destruction all participates in the dance of becoming. The early universe, it seems, was mastering this cosmic choreography when it was still remarkably young. The redshift of JD's GSD 14-0, measured at approximately 14.18, places it at a time when the universe was expanding more rapidly than today, driven by the mysterious force we call dark energy. This expansion stretches space itself, and with it, the wavelengths of light travelling through the cosmos. The deeper we look into space, the more dramatically this cosmic redshift affects the light we observe. Perhaps the most remarkable aspect of this ancient galaxy is what it tells us about the chemical evolution of the universe. The detection of oxygen in JD's GSC 14-0 represents more than just a measurement. It's evidence of an entire stellar life cycle that had already played out when the universe was in its cosmic infancy. Oxygen is forged in the nuclear furnaces of massive stars through a process called stellar nucleosynthesis. These stellar alchemists transform hydrogen and helium, the primary products of the Big Bang, into heavier elements through nuclear fusion reactions that occur at temperatures exceeding 100 million degrees Celsius. When these massive stars reach the end of their lives, they explode as supernovas, scattering their newly created elements into space. The presence of oxygen in such an early galaxy means that at least one generation of massive stars had already completed this cosmic cycle of birth, nuclear burning, and explosive death. These stellar pioneers had to form from the primordial hydrogen and helium left over from the Big Bang, live their brief but brilliant lives, and then seed their environment with heavy elements, all within the first few 100 million years of cosmic history. This timeline presents a significant challenge to our understanding of stellar evolution. Massive stars live fast and die young, but even the most massive stars require millions of years to exhaust their nuclear fuel. The most efficient theoretical models struggle to compress the formation, evolution, and death of multiple stellar generations into the time frame available in the early universe. Yet there's something profoundly beautiful about this cosmic urgency. The early universe appears to have been a place of intense creativity and rapid transformation, where the fundamental processes that would shape all future cosmic evolution were being established at breakneck speed. It's as if the cosmos was eager to explore all the possibilities of existence, rushing to create the elements and structures that would eventually give rise to planets, life, and consciousness. Reflect for a moment on your own relationship with time and transformation. How often do you surprise yourself with the speed of your own growth and change? The universe, it seems, has been demonstrating from its very beginning that remarkable transformations can occur more quickly than we might expect. As we peer into the cosmic past through the lens of the James Webb Space Telescope, we approach what astronomers call the cosmic dark ages, a period between the formation of the cosmic microwave background and the ignition of the first stars. This epoch remains largely hidden from our view, shrouded in neutral hydrogen that absorbed most forms of electromagnetic radiation. JADES GSZ 14-0 sits at the very edge of this mysterious period, a beacon of light emerging from the cosmic darkness. But it's not alone. Webb has discovered numerous other galaxies from similar epochs, each one challenging our assumptions about early cosmic evolution. These discoveries suggest that the transition from the Dark Ages to cosmic dawn was more rapid and dramatic than previously thought. The implications extend far beyond astronomy. These early galaxies represent some of the first large-scale structures to emerge from the quantum fluctuations that existed in the primordial universe. In a very real sense, they are the descendants of quantum mechanical uncertainties that were inflated to cosmic scales during the universe's first moments of existence. This connection between the quantum realm and cosmic structure formation remains one of the most profound mysteries in physics. How do microscopic quantum fluctuations give rise to galaxies containing billions of stars? How does the probabilistic nature of quantum mechanics transition into the seemingly deterministic behavior of large-scale cosmic structures? Some interpretations suggest that the measurement problem in quantum mechanics might have played a role in the early universe, with the act of cosmic expansion itself serving as a kind of universal measurement that collapsed quantum superpositions into classical structures. This remains highly speculative, but it illustrates how the discovery of early massive galaxies connects to fundamental questions about the nature of reality itself. As you consider these connections between the quantum and cosmic realms, you might notice how they resonate with questions about your own existence. How do the microscopic processes in your brain give rise to consciousness? How do quantum mechanical events in your neural networks create the experience of thought and awareness? These parallels between cosmic and personal mystery remind us that we are part of a universe that remains deeply enigmatic at every scale. Behind the visible splendour of J-Day's GSZ 14.0 lies an invisible partner in the cosmic dance. Dark matter, that mysterious substance that comprises roughly 85% of all matter in the universe, provides the gravitational scaffolding upon which all cosmic structures are built. Understanding the role of dark matter in early galaxy formation is crucial to solving the puzzle of how such massive galaxies could emerge so quickly. In the standard model of cosmology, dark matter began clumping together shortly after the Big Bang, forming vast halos that would eventually host the first galaxies. These dark matter halos act as gravitational wells, attracting ordinary matter and providing the framework for star formation. The larger and denser the dark matter halo, the more rapidly a galaxy can grow. But the existence of galaxies like J-Day's GSZ 14-0 suggests that either dark matter was more efficiently concentrated in the early universe, or that our understanding of how dark matter behaves on galactic scales needs refinement. Some theoretical models propose that dark matter might have interactions beyond gravity that we haven't yet discovered, allowing it to cool and condense more rapidly than pure gravitational collapse would permit. Another possibility involves the nature of dark matter itself. While we typically think of dark matter as cold and slow-moving, some models suggest it might have been warmer in the early universe, allowing different clustering behaviour that could facilitate rapid galaxy formation. These ideas remain highly speculative, but they demonstrate how the discovery of early massive galaxies is pushing us to reconsider our most fundamental assumptions about the invisible universe. The dance between dark matter and ordinary matter in the early universe was likely far more complex than our current simulations can capture. Gas flowing into dark matter halos must cool efficiently to form stars, but this cooling depends on the presence of heavy elements that are produced by stellar nucleosynthesis. The first galaxies faced a chicken and egg problem. They needed stars to produce the elements necessary for efficient cooling, but they needed efficient cooling to form stars in the first place. Perhaps the early universe found creative solutions to this dilemma. Maybe the first stars were more massive and luminous than typical stars today, producing heavy elements more rapidly and efficiently. Or perhaps dark matter halos in the early universe were denser and more concentrated, providing stronger gravitational wells that could overcome the inefficiencies of primordial gas cooling. As you reflect on this invisible cosmic architecture, consider how much of your own life is shaped by forces and influences you cannot directly perceive. The thoughts and emotions that guide your decisions emerge from neural processes you're rarely aware of. The cultural and social forces that shape your worldview operate largely below the threshold of conscious recognition. Like the universe itself, your existence is supported by an invisible scaffolding that makes visible experience possible. The discovery of JADES GSZ 14.0 is more than a single remarkable finding. It represents the opening of a new chapter in our exploration of cosmic history, made possible by the unprecedented capabilities of the James Webb Space Telescope. As this remarkable instrument continues its observations, we can expect more surprises that will challenge and refine our understanding of the universe's youth. Future observations will probe even deeper into cosmic time, potentially discovering galaxies that formed even earlier than JDES GS 14-0. Each new discovery will add another piece to the puzzle of early cosmic evolution, helping us understand how the universe transitioned from the simple, smooth state revealed by the cosmic microwave background to the rich, complex structure we observe today. The spectroscopic analysis of these ancient galaxies will become increasingly sophisticated, allowing astronomers to measure the abundances of multiple elements and trace the chemical evolution of the early universe in unprecedented detail. We may discover that the first stars and galaxies operated under physical conditions so different from today that they require new theoretical frameworks to understand. But perhaps most intriguingly, these observations will help us understand the relationship between the first galaxies and the cosmic structures that followed. How did these early massive galaxies influence their surroundings? Did they seed the formation of even larger structures? Or did they represent evolutionary dead ends that were eventually overwhelmed by later cosmic evolution? The answers to these questions will reshape our understanding not just of the early universe, but of cosmic evolution as a whole. They will help us understand how the cosmos developed from its initial simplicity to the breathtaking complexity we observe today, and they may even provide clues about the universe's ultimate fate. As we stand on the threshold of these discoveries, take a moment to appreciate the profound privilege of living at a time when such questions can be asked and potentially answered. Throughout most of human history, the origin and evolution of the universe remained completely mysterious. Today, we possess instruments capable of observing the cosmos when it was less than 300 million years old, revealing secrets that no previous generation could have imagined. This ongoing revelation of cosmic mystery invites us to maintain a sense of wonder and humility in the face of the unknown. Just as JDES GS Z14-0 surprised us with its unexpected properties, the universe continues to hold surprises we haven't yet imagined. The greatest discoveries often come not from confirming what we expect to find, but from encountering what we never thought possible. In our continuing exploration of these cosmic mysteries, we'll examine how the latest discoveries are revealing connections between the largest and smallest scales of existence, from the quantum realm to the cosmic web. But for now, let this ancient galaxy remind us that we live in a universe far stranger and more wonderful than we ever dared imagine, where the impossible becomes possible and the past continues to surprise us with gifts of knowledge we're only beginning to unwrap. The journey into cosmic mystery is far from over. As Webb continues to peer into the depths of space and time, as new telescopes join the quest for understanding, and as theoretical models evolve to accommodate new discoveries, we can expect our picture of the early universe to become both clearer and more mysterious. Each answer reveals new questions, each solution opens new puzzles, and each discovery reminds us that the cosmos is more creative, more dynamic, and more surprising than we ever imagined possible. As we drift deeper into this cosmic meditation, a profound realization begins to emerge from the depths of theoretical physics. The massive galaxy we've been contemplating, JDES GS 14-0, didn't arise from nothing. Its origins can be traced back to the very first moments after the Big Bang, when the universe existed in a state so foreign to our everyday experience that it challenges the boundaries of imagination itself. In those primordial instants, when the cosmos was smaller than a grain of sand and hotter than the core of any star, quantum mechanical fluctuations danced through the fabric of space-time. These weren't just minor ripples in an otherwise smooth universe. They were the seeds of everything that would follow, tiny variations in density and energy that would eventually grow into galaxies, stars, and the very atoms that compose your body at this moment. Take a breath and consider the profound implications of this connection. The light reaching your eyes from your screen, the oxygen filling your lungs, the thoughts flowing through your consciousness, all of these phenomena can trace their lineage back to quantum fluctuations that occurred when the universe was less than a second old. You are intimately connected to those first moments of cosmic existence in ways that transcend metaphor. The process by which these microscopic quantum seeds grew into cosmic structures remains one of the most beautiful examples of emergence in all of physics. During a period called cosmic inflation, these quantum fluctuations were stretched to astronomical scales in a fraction of a second. What began as uncertainty at the subatomic level became the blueprint for the cosmic web that spans billions of light years. But here's where the story becomes even more intriguing. Some interpretations suggest that the quantum nature of these primordial fluctuations never fully disappeared. Even as they grew to cosmic proportions, they may have retained certain quantum properties that influenced how matter clumped together in the early universe. This remains unproven, but it hints at a universe where quantum mechanics and cosmic structure formation are far more intimately connected than we previously imagined. The discovery of early massive galaxies like JD's GSZ 14-0 forces us to reconsider this quantum cosmic connection. Perhaps the fluctuations that gave rise to such massive early structures were stronger or more coherent than our standard models predict. Or perhaps the process of structure formation in the early universe involved quantum mechanical effects that we're only beginning to understand. As you contemplate the vast scales of space and time we've been exploring, you might notice something remarkable happening in your own awareness. The ability to hold these cosmic concepts in your mind, to imagine galaxies forming billions of years ago, represents a profound feat of consciousness that we rarely pause to appreciate. Your brain evolved over millions of years to navigate the immediate challenges of survival, somehow possesses the capacity to comprehend structures billions of times larger than Earth, and events that occurred long before our solar system existed. This cognitive ability to transcend the boundaries of direct experience is perhaps as mysterious as the cosmic phenomena we're studying. Neuroscientists are beginning to understand how the brain creates our sense of time and space. Networks of neurons fire in complex patterns, creating internal models of reality that allow us to navigate both the physical world and abstract conceptual realms. When you imagine the early universe or visualize the journey of ancient photons, your brain is performing calculations and creating representations that exist nowhere else in the known universe. This capacity for cosmic contemplation raises profound questions about the nature of consciousness itself. How does the electrochemical activity in your neural networks give rise to the subjective experience of wonder you feel when contemplating distant galaxies? How does matter organized in the particular patterns of your brain become aware of its own cosmic origins? Some interpretations suggest, though this remains highly speculative, that consciousness might be a fundamental feature of the universe, rather than merely an emergent property of complex neural networks. In this view, The capacity for awareness exists at some level throughout the cosmos, manifesting in different forms as matter organizes itself into increasingly complex structures. While no scientific consensus exists on this interpretation, it offers a poetic way of understanding your connection to the cosmic story. The atoms in your brain were forged in stellar furnaces, scattered through space by exploding stars, and eventually assembled into the neural networks that allow you to contemplate your own cosmic heritage. In a very real sense, the universe has organized itself in such a way that it can become aware of its own existence through your consciousness. The more we learn about JDES GSZ 14-0 and other early massive galaxies, the more we realize that the universe's capacity for creating complex, beautiful structures emerged remarkably early in cosmic history. This galaxy isn't just a collection of stars and gas. It's a masterpiece of cosmic architecture, a testament to the universe's innate creativity and drive toward complexity. When astronomers analyze the detailed structure of this ancient galaxy, they find evidence of organized star formation, chemical evolution, and gravitational dynamics that rival what we observe in much later epochs. The galaxy appears to have spiral arms or other structured features that suggest sophisticated gravitational interactions were already shaping galactic morphology when the universe was still in its infancy. This early emergence of cosmic complexity challenges our assumptions about the relationship between time and structure formation. We often think of the universe as slowly building complexity over billions of years, gradually assembling simple components into more elaborate systems. But JD's GSZ 14-0 suggests that the cosmos was capable of creating remarkable complexity much earlier than we expected. Perhaps this shouldn't surprise us when we consider the patterns we observe throughout nature. Complexity often emerges suddenly and dramatically rather than gradually. A seed grows slowly for weeks, then suddenly bursts into bloom. A child develops language skills gradually, then experiences rapid leaps in linguistic capability. The universe itself may follow similar patterns of punctuated complexity. As you reflect on these cosmic patterns of emergence, notice how they mirror processes in your own life and development. How often do you experience periods of gradual change, followed by sudden insights or transformations? The universe seems to operate according to similar rhythms of slow preparation, followed by rapid manifestation. The detection of organized structure in such an early galaxy also tells us something profound about the nature of information in the universe. The patterns we observe in JDES GSZ 14-0 represent information that has been preserved across more than 13 billion years of cosmic evolution. The arrangement of stars, the distribution of elements, the overall morphology of the galaxy, all of these features encode information about conditions in the early universe. One of the most remarkable aspects of our ancient galaxy involves the story written in its starlight. The spectrum of light from JD's GS 14-0 reveals the signatures of multiple stellar populations, each with its own chemical fingerprint. This diversity tells us that several generations of stars had already lived and died by the time we observe this galaxy, each generation building upon the chemical legacy of its predecessors. The first generation of stars in the universe, often called population 3 stars, were fundamentally different from the stars we observe today. These primordial suns formed from pure hydrogen and helium, the only elements available in the aftermath of the Big Bang. They were likely much more massive than typical modern stars, burning brilliantly but briefly, ending their lives in spectacular supernova explosions that scattered the first heavy elements through space. The second generation of stars, enriched with these newly created elements, could form planets and more complex stellar systems. By the third generation, the universe had accumulated enough heavy elements to support the formation of rocky planets and the complex chemistry necessary for life as we know it. The light from JDES GS 14-0 suggests that this stellar succession was already well underway when the universe was less than 300 million years old. This rapid stellar evolution in the early universe presents fascinating questions about the pace of cosmic development. If stellar generations were turning over so quickly in the universe's youth, what does this tell us about the conditions that existed during cosmic dawn? Were the first stars more massive and short-lived than our models predict? Did they form in denser environments that accelerated their evolution? Take a moment to consider your own connection to this stellar genealogy. The iron in your blood was forged in the core of a massive star that exploded billions of years ago. The calcium in your bones was created in stellar furnaces and scattered through space by supernova explosions. The oxygen you breathe was produced by multiple generations of stars, each contributing to the chemical complexity that makes life possible. This stellar ancestry connects you directly to the cosmic story we've been exploring. You are not separate from the universe, observing it from the outside. You are the universe becoming conscious of itself, made of stellar material, organized in such a way that it can contemplate its own origins and evolution. As we approach the limits of what the James Webb Space Telescope can detect, we encounter one of the most profound boundaries in all of science, the edge of the observable universe. This isn't a physical edge like the shore of an ocean. Rather, it's a horizon in time, the farthest point into the past that any telescope can peer, no matter how advanced. This cosmic horizon is set by the speed of light and the age of the universe. Light from more distant objects simply hasn't had time to reach us since the Big Bang occurred. We exist within a sphere of observability, surrounded by regions of space and time that remain forever beyond our direct observation. JD's GS Z14-0 sits tantalizingly close to this ultimate boundary, offering us glimpses of cosmic conditions that existed near the very limits of what can be known through direct observation. But this observational boundary raises profound philosophical questions. If there are regions of the universe we can never observe, what does this mean for our understanding of reality itself? How do we make sense of a cosmos that extends beyond the reach of any possible measurement or observation? Some interpretations suggest that the unobservable universe might be fundamentally different from the portion we can study. Perhaps different physical constants apply in distant regions, or perhaps entirely different forms of matter and energy exist beyond our cosmic horizon. This remains purely speculative, but it reminds us that our scientific understanding is necessarily limited by the boundaries of observation. The humility this cosmic horizon imposes might actually be one of its greatest gifts. It reminds us that reality extends far beyond what we can directly perceive or measure. Just as the discovery of JD's GSC 14-0 surprised us with its unexpected properties, the unobservable universe likely contains phenomena that would challenge our most fundamental assumptions about the nature of existence. As you sit with this idea of cosmic boundaries, notice how it might relate to the boundaries of your own knowledge and experience. How much of reality remains hidden from your direct perception? What mysteries exist in the depths of your own consciousness, in the quantum realm beneath everyday experience, or in the vast reaches of cosmic space and time. Returning to the quantum origins of cosmic structure, we encounter one of the most beautiful examples of how the smallest and largest scales of reality interconnect. The quantum fluctuations that seeded the formation of JD's GSZ 14-0 operated according to principles that seem almost magical when viewed from our everyday perspective. In the quantum realm, particles can exist in multiple states simultaneously, a phenomenon called superposition. They can be instantaneously connected across vast distances through quantum entanglement. They can tunnel through barriers that should be impenetrable according to classical physics. These quantum properties seem divorced from the familiar world of galaxies and stars, yet they played a crucial role in shaping cosmic structure. During cosmic inflation, quantum fluctuations were amplified to macroscopic scales while potentially retaining some of their quantum character. This process remains one of the most mysterious aspects of early cosmic evolution. How exactly do quantum mechanical uncertainties transform into the classical structures we observe in today's universe? The boundary between quantum and classical reality remains one of the deepest puzzles in physics. Some interpretations suggest, though this remains unproven, that quantum effects might persist at much larger scales than previously thought. Perhaps the formation of early massive galaxies like JD's GSZ 14-0 involved quantum mechanical processes that we don't yet understand. This is a speculative idea, not a proven scientific fact, but it illustrates how the discovery of unexpected cosmic phenomena can push us to reconsider our most basic assumptions about reality. The quantum nature of the universe's foundations also raises intriguing questions about the role of information in cosmic evolution. In quantum mechanics, information plays a fundamental role, with the act of measurement causing quantum states to collapse into definite outcomes. Some theorists speculate that the universe itself might be understood as an information processing system, with cosmic evolution representing the flow and transformation of quantum information on the largest possible scales. While these ideas remain highly theoretical, they offer a perspective on cosmic evolution that emphasizes the fundamental role of information and observation in shaping reality. In this view, the universe isn't just a collection of matter and energy evolving according to physical laws. It's an integrated system of information processing, with each observation and interaction contributing to the ongoing evolution of cosmic structure. The chemical composition of JD's GSZ 14-0 tells a story that reads like cosmic poetry. Each element detected in its spectrum represents a chapter in the universe's chemical evolution, from the simplest hydrogen atoms forged in the Big Bang to the complex heavy elements created in stellar furnaces. This chemical archaeology allows us to reconstruct the history of stellar birth and death that preceded the galaxy's formation. The abundance patterns observed in this ancient galaxy reveal something remarkable about the efficiency of early stellar nucleosynthesis. The ratios of different elements suggest that the first stars were not only massive and short-lived, but also extraordinarily effective at producing and distributing heavy elements. This chemical enrichment happened much faster than our standard models predict, adding another layer to the mystery of early cosmic evolution. Carbon, nitrogen, and oxygen, the building blocks of organic chemistry, were already present in significant quantities when JD's GSZ 14-0 formed. This means that the chemical foundations for life, as we know it, were established remarkably early in cosmic history. While this doesn't mean that life existed in the early universe, it does suggest that the chemical prerequisites for biological complexity emerged much sooner than previously thought. The presence of these elements in such an early galaxy also tells us something profound about the interconnectedness of cosmic evolution. The same nuclear processes that create the elements necessary for life also power the stellar engines that illuminate galaxies. The same supernova explosions that scatter heavy elements through space also trigger the formation of new generations of stars. Chemistry, stellar evolution, and galactic structure formation are all aspects of a single, integrated cosmic process. As you breathe in this moment, consider that the oxygen entering your lungs was created in stellar cores billions of years ago. The carbon in your DNA was forged in the nuclear furnaces of ancient stars and scattered through space by stellar explosions. The calcium in your bones, the iron in your blood, the phosphorus in your thoughts, all of these elements tell a story that connects you directly to the cosmic chemical evolution we observe in distant galaxies like JD's GSZ 14-0. This chemical kinship with the cosmos isn't just a poetic metaphor, it's a literal truth that places you at the center of an ongoing cosmic story. You're made of processed starlight, organized into patterns complex enough to contemplate the very stars that created you. In your conscious awareness of this ancient galaxy, the universe achieves a kind of self-recognition that spans billions of years and countless light years of space. As we near the end of our contemplative journey through cosmic deep time, a curious pattern begins to emerge. The discovery of JD's GSZ 14-0 and other early massive galaxies doesn't just tell us about the past. It also provides clues about the future evolution of the universe and our place within it. The rapid structure formation we observe in the early cosmos might be a preview of processes that continue to operate on longer timescales. The efficiency with which early galaxies assembled mass and formed stars suggests that the universe possesses an inherent drive toward complexity and organization. This tendency toward increasing structure and sophistication didn't end with the formation of the first galaxies. It continues today in the ongoing evolution of cosmic structure, the development of planetary systems, and the emergence of life and consciousness. When we observe JD's GSZ 14-0, we're not just looking back in time, we're also looking at a preview of the universe's creative potential. The same processes that allowed this ancient galaxy to form so quickly and efficiently continue to operate throughout the cosmos, creating new structures and new possibilities for complexity and beauty. The universe that surprised us with rapid early galaxy formation continues to surprise us with its ongoing creativity. Future observations with even more advanced telescopes will undoubtedly reveal more secrets about the early universe and its connection to later cosmic evolution. We may discover that the rapid formation of massive early galaxies was just the beginning of a universe-wide pattern of accelerated development and unexpected creativity. Each new discovery will add another verse to the cosmic poem we've been reading in the ancient light of distant galaxies. But perhaps the most profound implication of these discoveries relates to consciousness itself. The same universe that created massive galaxies in its youth also created the conditions for the emergence of life and awareness. The chemical elements forged in early stellar furnaces eventually became the building blocks of biological systems capable of contemplating their own cosmic origins. As you sit here, aware of these cosmic connections, you represent the universe's most remarkable achievement. You are matter organized in such a way that it can become conscious of its own existence and evolution. Through your awareness, the cosmos achieves a form of self-knowledge that spans from quantum fluctuations in the first moments after the Big Bang to the emergence of consciousness billions of years later. The light from James GSZ 14-0 that reaches your eyes through the Webb telescope carries information that has been travelling for over 13 billion years. In your conscious perception of this ancient light, you complete a circuit of cosmic communication that connects the earliest epochs of the universe to this present moment of awareness. You are not just observing the cosmos, you are the cosmos observing itself. As we continue our gentle drift through this cosmic mystery, something extraordinary begins to reveal itself in the spaces between what we can measure and observe. The James Webb Space Telescope captures images of JD's GSZ 14-0 during specific moments of observation. But what happens to this ancient galaxy during the vast stretches of time when no human eye is turned toward it? This question touches something fundamental about the nature of reality itself. In quantum mechanics, there exists a principle that has puzzled physicists for nearly a century. The act of observation appears to play a crucial role in determining the properties of quantum systems. Before measurement, particles exist in what we call superposition, a state of multiple possibilities existing simultaneously. Only when observed do they seem to collapse into definite states with specific properties. Now, this quantum measurement problem remains hotly debated among physicists, and no scientific consensus exists about what it truly means for macroscopic objects like galaxies. But the parallel is intriguing to contemplate. When astronomers point Webb toward JD's GSZ 14-0, they're not just passively receiving ancient light, they're participating in a cosmic conversation that spans 13 billion years, completing an act of observation that began when the first stars in that distant galaxy ignited their nuclear furnaces. Take a moment to consider your own relationship with observation and awareness. How much of your daily experience unfolds without your conscious attention? The beating of your heart, the processing of light by your retinal cells, the countless neural computations that create your sense of continuous consciousness. Most of reality operates beyond the threshold of direct observation, yet it continues to unfold with remarkable precision and beauty. Some interpretations suggest, though this remains unproven, that consciousness might play a more fundamental role in the structure of reality than we typically imagine. Not in the sense that your thoughts directly influence distant galaxies, but rather that awareness itself might be woven into the fabric of existence in ways we're only beginning to explore. The gap between quantum mechanics and our understanding of cosmic scale phenomena represents one of the deepest mysteries in physics. How do the probabilistic rules that govern atomic and subatomic particles give rise to the apparently deterministic behaviour of stars and galaxies? The discovery of early massive galaxies like JD's GSZ 14-0 adds another layer to this puzzle, suggesting that the transition from quantum to classical behaviour in the early universe might have been more complex than our current theories predict. Every photon reaching us from JD's GSZ 14-0 carries within itself a perfect memory of the conditions that existed when it was first emitted. This ancient light has travelled for over 13 billion years, passing through regions of space that have expanded, cooled and evolved dramatically since its journey began. Yet somehow, encoded in its wavelength and polarization, lies information about stellar temperatures, chemical abundances, and galactic dynamics from cosmic dawn. This preservation of information across such vast scales of space and time reveals something profound about the nature of the universe itself. Information, it seems, is remarkably persistent. Once encoded in the structure of electromagnetic radiation, it can survive journeys that span significant fractions of cosmic history. The light waves that left JD's GSZ 14-0 when the universe was young have maintained their coherence and information content across distances that dwarf human comprehension. Consider how this mirrors the persistence of information in your own experience. Memories formed years or decades ago can suddenly resurface with startling clarity, triggered by a scent, a sound, or a particular quality of light. The neural patterns that encode these memories have persisted through countless cycles of cellular renewal and molecular replacement. In a very real sense, you are a biological system capable of preserving and retrieving information across time, much like the cosmic light that preserves memories of ancient stellar processes. The spectroscopic analysis of this primordial light reveals layers of information that would have been completely inaccessible to earlier generations of astronomers. Modern instruments can detect the signatures of individual elements, measure stellar velocities, and even infer the presence of magnetic fields in galaxies that formed when the universe was a fraction of its current age. Each photon becomes a messenger, carrying news from an epoch so remote that it challenges our ability to comprehend the depths of cosmic time. But perhaps most remarkably, this ancient light interacts with your consciousness in this very moment. The electromagnetic radiation that began its journey when the first complex molecules were forming in interstellar space now stimulates the quantum processes in your visual cortex, creating the subjective experience of perceiving distant starlight. You are not just observing the early universe, you are participating in its ongoing story through the act of conscious awareness. As we examine the structural properties of JD's GSZ 14-0 more closely, we encounter features that shouldn't exist according to our standard models of galaxy formation. The galaxy displays evidence of organized spiral structure, central concentration, and even potential signs of a supermassive black hole, all characteristics that should have taken much longer to develop in that early universe. The presence of what appears to be a central supermassive black hole presents a particularly intriguing puzzle. These cosmic monsters, containing millions or billions of times the mass of our Sun, somehow existed when the universe was less than 300 million years old. But how do such massive objects form so quickly? Current theories struggle to explain how black holes could grow from stellar mass seeds to supermassive proportions in such a short time frame. Some theoretical models propose that primordial black holes formed directly from the collapse of dense regions in the early universe might have provided the seeds for rapid growth. Others suggest that the first stars were so massive that they collapsed directly into intermediate mass black holes, which then merged and accumulated matter at extraordinary rates. These remain speculative ideas, not proven scientific facts, but they illustrate how the discovery of early massive galaxies is pushing the boundaries of theoretical astrophysics. The organized structure visible in JD's GSZ 14-0 also challenges our understanding of how galactic morphology develops over time. The formation of spiral arms requires complex gravitational dynamics and stellar feedback processes that should take hundreds of millions of years to establish. Yet here we observe what appears to be mature galactic structure at an epoch when such organization shouldn't yet exist. As you contemplate these architectural impossibilities, notice how they resonate with patterns of emergence in your own life. How often do complex insights or creative solutions appear suddenly, seemingly without the gradual build-up you might expect? The early universe appears to have been a realm where emergence and self-organization operated according to principles we don't yet fully understand. The galaxy's ability to maintain coherent structure while forming stars at such a rapid rate also suggests sophisticated regulatory mechanisms were already operating in the cosmic dawn. Star formation typically involves complex feedback loops between stellar birth, stellar death, and the heating and cooling of interstellar gas. The fact that JD's GSC 14-0 achieved such massive proportions implies these regulatory processes were remarkably efficient from the very beginning. The environment in which JD's GSC 14-0 formed was utterly unlike the cosmic neighborhood we inhabit today. The early universe was denser, hotter, and filled with primordial gas that had never been processed through stellar interiors. Understanding this ancient cosmic ecology is crucial to comprehending how such massive galaxies could assemble so rapidly in conditions that seem inhospitable to complex structure formation. The cosmic web of dark matter filaments that provides the scaffolding for galaxy formation was still in its infancy when JD GSC 14-0 emerged. The largest dark matter halos were just beginning to collapse and virialize, creating gravitational wells capable of capturing and concentrating ordinary matter. Yet somehow, this process occurred with sufficient efficiency to create the massive stellar systems we observe in early galaxies. The gas falling into these primordial dark matter halos faced significant challenges in cooling and condensing into stars. Without the heavy elements produced by stellar nucleosynthesis, the cooling mechanisms available to primordial gas were far less efficient than those operating in the modern universe. This should have slowed star formation dramatically, yet we observe evidence of vigorous stellar birth in the earliest galaxies. Perhaps the early universe developed alternative cooling mechanisms that we haven't yet identified in our theoretical models. Maybe magnetic fields played a more important role in early structure formation than we currently understand. Or possibly the dark matter itself had properties in the early universe that enhanced its ability to concentrate ordinary matter and facilitate rapid galaxy assembly. Take a breath and consider how this cosmic ecology might reflect principles that operate in your own life and development. Complex systems, whether biological or cosmic, often emerge through the interaction of multiple environmental factors that must align in precisely the right ways. The rapid emergence of massive early galaxies suggests that the young universe was extraordinarily fertile ground for the development of complex structures. The chemical ecology of the early universe was also fundamentally different from today. The absence of heavy elements meant that dust grains, which play a crucial role in modern star formation by facilitating gas cooling and providing surfaces for molecular formation, were essentially non-existent. Early stars had to form through purely gravitational collapse of primordial hydrogen and helium, a process that should have been far less efficient than contemporary star formation. As our exploration of this cosmic mystery deepens, we begin to encounter something that transcends the mere accumulation of scientific facts. The discovery of JADES GSZ 14-0 represents more than just another data point in our catalogue of distant galaxies. It reveals the universe as a far more creative and dynamic entity than our theories had previously suggested. This creativity isn't limited to the cosmic realm. The same principles of emergence, self-organization, and rapid development that allowed massive galaxies to form in the universe's youth continue to operate throughout nature. From the sudden crystallization of supersaturated solutions to the rapid emergence of new species in evolutionary history, the universe demonstrates a persistent capacity for surprise and innovation. Consider how this cosmic creativity might manifest in your own experience of consciousness. Thoughts and insights often emerge spontaneously, without the gradual build-up you might expect from purely mechanistic processes. The same universe that surprised us with rapid early galaxy formation continues to surprise us through the emergence of awareness, creativity, and understanding in conscious beings. The mathematical elegance underlying these cosmic phenomena also deserves our wonder. The same equations that describe the behavior of quantum particles also govern the evolution of galactic structures across billions of years. This deep mathematical unity suggests that the universe operates according to principles that transcend the apparent differences between microscopic and macroscopic realms. Some interpretations suggest, though this remains unproven, that consciousness itself might be understood as another expression of the universe's fundamental creativity. The same processes that allow matter to self-organize into complex structures like galaxies and stars might also give rise to the even more complex patterns of neural activity that create subjective experience and awareness. As you sit with these ideas, notice how they invite a sense of participation rather than mere observation. You're not separate from the cosmic processes we've been exploring. You are one of their most remarkable expressions, matter organized in such a way that it can contemplate its own origins and marvel at its own complexity. We stand now at a threshold in our understanding of cosmic evolution, much like astronomers stood at the threshold of discovery when they first pointed the James Webb Space Telescope toward the distant reaches of space and time. The detection of JD's GSZ 14-0 and other early massive galaxies represents just the beginning of a revolution in our comprehension of how the universe developed its current structure and complexity. Future observations will undoubtedly reveal more surprises that challenge our theoretical frameworks and expand our appreciation for the universe's creative capacity. Each new discovery will add another piece to the cosmic puzzle, while simultaneously revealing how much we still don't understand about the fundamental nature of existence. The questions raised by early massive galaxies extend far beyond astronomy and cosmology. They touch on fundamental issues in physics, philosophy, and even consciousness studies. How does complexity emerge from simplicity? What role does information play in cosmic evolution? Are there principles of self-organization that operate across all scales of existence, from quantum systems to galactic structures to conscious minds? These questions don't have easy answers, and perhaps that's precisely the point. The universe seems designed to maintain a sense of mystery and wonder, always revealing enough to keep us engaged while withholding enough to preserve the sense of awe that drives scientific discovery. The cosmic horizon that limits our observations ensures that there will always be more to discover, more to question, more to contemplate. As you reflect on these cosmic mysteries, allow yourself to feel the profound privilege of existing at a time when such questions can be asked and potentially answered. Throughout most of human history, the origin and evolution of the universe remained completely beyond the reach of empirical investigation. Today, we possess instruments capable of detecting the light from galaxies that formed when the cosmos was still in its infancy. This technological capability represents just one expression of the universe's ongoing creativity. The same cosmic processes that created the first stars and galaxies also created the conditions for the emergence of life, consciousness, and the scientific instruments that allow us to study our own cosmic origins. In a very real sense, the universe has evolved to the point where it can study itself through beings like us. In the ancient light from JDES GSZ 14-0, we encounter something that functions as a kind of cosmic mirror, reflecting not just the conditions of the early universe, but also the nature of our own existence as conscious observers. This galaxy, impossibly massive and mature for its age, challenges us to reconsider our assumptions about time, development, and the relationship between potential and actualization. The rapid formation of complex galactic structures in the early universe suggests that potential for organization and complexity was somehow encoded in the fundamental properties of matter and energy from the very beginning. The quantum fluctuations that seeded galaxy formation weren't random perturbations, but rather expressions of deeper organizational principles that we're only beginning to understand. This perspective invites us to consider consciousness itself as another expression of the universe's inherent tendency toward complexity and self-organization. The same creative forces that assembled the first galaxies in cosmic dawn continue to operate through the emergence of awareness, understanding, and the capacity for cosmic contemplation. When you observe the image of JDES GSZ 14-0 captured by the Webb telescope, you're participating in a process of cosmic self-recognition that spans billions of years. The light that left that galaxy when the universe was young now interacts with the neural networks in your brain, creating the subjective experience of perceiving ancient starlight. In this moment of awareness, the universe achieves a form of self-knowledge that bridges the gap between cosmic dawn and the present moment. The mathematical precision required for this cosmic conversation is breathtaking to contemplate. The photons that began their journey billions of years ago had to maintain their coherence and information content across vast distances of expanding space. The Webb telescope had to be positioned with extraordinary precision to capture this ancient light. Your visual system had to evolve over millions of years to process electromagnetic radiation and create the experience of sight. All of these processes had to unfold with remarkable coordination for this moment of cosmic recognition to occur. You are not just observing the early universe, you are completing a circuit of communication that began when the first stars ignited in distant galactic nurseries billions of years before Earth existed. The equations that describe gravitational collapse, stellar nucleosynthesis, and cosmic expansion aren't just computational tools for making predictions about astronomical phenomena. They represent profound insights into the fundamental nature of reality itself. When we contemplate the elegant mathematical relationships that allow matter to self-organize into galaxies, stars, and eventually conscious beings, we encounter something that feels almost like cosmic music made manifest in physical form. This mathematical elegance suggests that the universe operates according to principles that transcend the apparent randomness and chaos we sometimes observe at smaller scales. The same deep symmetries that govern the behavior of subatomic particles also shape the evolution of cosmic structures across billions of years. There appears to be a fundamental unity underlying the apparent diversity of natural phenomena. Consider how this cosmic poetry might resonate in your own experience of consciousness. The thoughts and insights that emerge in your awareness often display an elegance and coherence that transcends the mechanical firing of individual neurons. Just as galaxies emerge from the gravitational interaction of countless particles, your conscious experience emerges from the coordinated activity of billions of neural elements organized in patterns of extraordinary complexity. Some interpretations suggest, though this remains a speculative idea rather than proven science, that consciousness might represent the universe's most sophisticated expression of its inherent tendency towards self-organization and complexity. The same creative principles that allow matter to assemble into galaxies might also give rise to the even more remarkable phenomenon of subjective experience and self-awareness. The discovery of early massive galaxies like JD's GSZ 14-0 reminds us that the universe has been composing this cosmic symphony for billions of years, with each new structure and each new level of complexity adding another movement to the ongoing composition. You are not separate from this cosmic music. You are one of its most beautiful and complex expressions. This ancient photons began their journey when the universe was young, but they arrive in this moment carrying information about stellar processes that occurred billions of years ago. In the act of observation, past and present collapse into a single moment of cosmic communication that transcends the linear flow of time as we normally experience it. The implications extend beyond astronomy into the realm of consciousness and existence itself. Your awareness of this ancient galaxy creates a direct connection between your present moment of consciousness and events that occurred long before Earth existed. Through the medium of light and the mechanism of perception, you participate in a form of time travel that brings the distant past into immediate present experience. This collapse of cosmic time into the eternal now of awareness offers a profound perspective on the nature of existence itself. The same light that reveals the early universe to our instruments also illuminates the deeper mystery of consciousness and its relationship to the physical cosmos. In perceiving ancient starlight, you demonstrate that awareness has the capacity to transcend the normal limitations of space and time. The light from JD's GSZ 14-0 has been travelling for over 13 billion years to reach this moment of conscious recognition. In your awareness of this ancient galaxy, you complete a cosmic conversation that began when the universe was still learning how to make its first complex structures. The same creative force that assembled massive galaxies in the cosmic dawn continues to work through your consciousness in this eternal present moment. The mystery that allowed complex structures to emerge so rapidly in the early universe also allows thoughts, insights, and moments of wonder to emerge in your awareness. You are not just observing the cosmos, you are the cosmos recognizing itself through the miracle of conscious perception. As our exploration draws toward its natural completion, we find ourselves not with final answers, but with an enriched sense of the questions that continue to guide cosmic discovery. The detection of JD's GSZ 14-0 represents just one chapter in an ongoing story of cosmic evolution that extends from the quantum realm to the largest scales of space and time. The impossibly massive galaxy we've been contemplating serves as a reminder that the universe consistently exceeds our expectations and challenges our theoretical frameworks. Each new discovery reveals how much we still don't understand about the fundamental processes that shape reality at every level. This ongoing mystery isn't a failure of scientific understanding, it's the engine that drives continued discovery and wonder. Future observations will undoubtedly reveal more early galaxies that challenge our assumptions about cosmic evolution. Advanced telescopes, now under construction, will peer even deeper into space and time, potentially detecting the very first stars and galaxies to form in the universe's youth. Each new instrument will expand our observational reach while simultaneously revealing new mysteries that await future investigation. But perhaps the most profound implication of these discoveries relates to consciousness itself and its role in the ongoing story of cosmic evolution. The same universe that surprised us with rapid early galaxy formation continues to surprise us through the emergence of awareness capable of contemplating its own origins. Through consciousness, the cosmos achieves a form of self-recognition that represents its most remarkable evolutionary achievement. As you carry these insights forward into your daily experience, remember that you are not separate from the cosmic processes we've been exploring. You're their most sophisticated expression, matter and energy organized in patterns complex enough to contemplate the universe that created them. The ancient light from distant galaxies illuminates not just the cosmic past, but the profound mystery of your own existence as a conscious being. The questions raised by early massive galaxies will continue to guide scientific investigation for generations to come. How do complex structures emerge from apparent simplicity? What role does consciousness play in cosmic evolution? Are there principles of self-organization that operate across all scales of existence? These questions invite continued exploration while preserving the sense of wonder that makes such exploration meaningful. As we drift further into this cosmic mystery, something remarkable begins to emerge from the depths of space itself. The massive presence of JD's GSZ 14-0 didn't just bend light during its ancient existence. It carved permanent ripples into the very fabric of space-time, gravitational waves that continue to propagate through the universe, even now, billions of years after their creation. These invisible messengers carry with them the memory of cosmic events that occurred when the universe was still learning the rules of existence. Imagine, if you will, that space-time itself possesses a kind of memory. Every massive object that has ever existed, every stellar explosion, every galactic collision, has left its signature written in the geometry of space itself. These gravitational memories don't fade with time. They continue to whisper through the cosmic dark, carrying information about events that occurred long before our solar system condensed from interstellar dust. The recent detection of gravitational waves by instruments like LIGO has opened an entirely new window into cosmic history. These ripples in space-time travel at the speed of light, but unlike electromagnetic radiation, they pass through matter virtually unimpeded. A gravitational wave that began its journey from the vicinity of JD's GSZ 14-0 billions of years ago might be passing through your body at this very moment, carrying with it the memory of stellar processes that occurred in the cosmic dawn. Take a breath and consider the profound intimacy of this connection. The same space-time that curves around your body right now also curves around distant galaxies billions of light years away. You exist within the same gravitational field that encompasses the entire observable universe. There is no separation, no boundary where your local space-time ends and cosmic space-time begins. You are woven into the gravitational fabric of existence itself. This gravitational memory extends beyond individual objects to encompass the large-scale structure of the universe. The cosmic web of dark matter filaments that provides scaffolding for galaxy formation has been shaped by gravitational interactions that began shortly after the Big Bang. The location where JDS-GS C14-0 formed was determined by gravitational forces that had been operating for hundreds of millions of years, concentrating matter in precisely the right configuration to allow rapid galaxy assembly. Some interpretations suggest, though this remains highly speculative, that information itself might be preserved in the gravitational structure of space-time. If true, this would mean that the universe possesses a kind of distributed memory system where every event leaves permanent traces in the geometry of space itself. The holographic principle in physics hints at such possibilities, proposing that all the information contained within a volume of space might be encoded on its boundary. Between the brilliant light of early galaxies like JDS-GS C14-0 lies something equally remarkable, yet invisible to our instruments. Dark matter, that mysterious substance comprising roughly 85% of all matter in the universe, participates in a kind of cosmic alchemy that transforms the simple into the complex, the uniform into the structured. Understanding this invisible architecture becomes crucial as we contemplate how massive galaxies could emerge so rapidly from the apparent chaos of the early universe. The gravitational scaffolding provided by dark matter operates according to principles we're only beginning to understand. Unlike ordinary matter, dark matter doesn't interact electromagnetically. It doesn't emit light, absorb radiation, or participate in the chemical processes that govern stellar evolution. Yet its gravitational influence shapes every aspect of cosmic structure formation, from the smallest galactic satellites to the largest galaxy clusters. In the epoch when JDS-GS C14-0 formed, dark matter had already begun the slow work of gravitational collapse, creating vast halos that would eventually host the first galaxies. These invisible structures grew through a process of hierarchical assembly, with smaller halos merging to form larger ones in a cosmic game of gravitational accumulation. The galaxy we observe today formed within one of these primordial dark matter cradles. But the relationship between dark matter and ordinary matter in early galaxy formation remains deeply mysterious. Current simulations suggest that the most massive dark matter halos should have formed gradually over hundreds of millions of years. Yet the existence of galaxies like JDS-GS C14-0 implies that either dark matter clustering was more efficient in the early universe, or that our understanding of dark matter itself needs fundamental revision. As you contemplate this invisible cosmic architecture, notice how it mirrors aspects of your own existence that operate beyond conscious awareness. The vast majority of neural processing in your brain occurs below the threshold of conscious recognition, yet these invisible processes shape every aspect of your subjective experience. Like dark matter in the cosmos, the unconscious dimensions of mind provide essential scaffolding for the emergence of conscious awareness. Some theoretical models propose that dark matter might possess properties we haven't yet discovered. Perhaps it underwent phase transitions in the early universe that enhanced its clustering behavior, or maybe dark matter interacts with itself through forces beyond gravity, allowing it to cool and condense more efficiently than purely gravitational collapse would permit. These remain speculative ideas rather than proven scientific facts, but they illustrate how the discovery of early massive galaxies challenges our understanding of cosmic architecture. As we examine the properties of JDS-GS C14-0 across multiple wavelengths of electromagnetic radiation, we discover something that speaks to the fundamental interconnectedness of physical processes operating across vastly different scales. The same physical laws that govern quantum interactions in atomic nuclei also determine the behavior of stellar atmospheres, galactic dynamics, and the large-scale evolution of cosmic structure. This unity of physical law across cosmic scales represents one of the most profound insights of modern science. The nuclear fusion reactions that power stars operate according to quantum mechanical principles first discovered in laboratory experiments. The gravitational dynamics that shape galactic structure follow mathematical relationships that also describe the behavior of planetary orbits. The electromagnetic radiation we detect from distant galaxies obeys the same wave equations that govern radio transmissions and visible light. Take a moment to appreciate the remarkable fact that the mathematical language used to describe subatomic particles also applies to objects billions of times larger and more massive. This suggests something fundamental about the nature of reality itself. The universe appears to be constructed according to consistent principles that transcend the apparent differences between microscopic and macroscopic phenomena. The spectroscopic analysis of JADESGSZ140 reveals this unity in action. The specific wavelengths of light emitted by hydrogen atoms in this distant galaxy are identical to those produced by hydrogen in terrestrial laboratories. The same quantum energy levels that determine atomic emission spectra operate consistently across billions of years of cosmic evolution and vast distances of space. This consistency of physical law has profound implications for our understanding of consciousness and its relationship to the physical universe. The same electromagnetic processes that create stellar spectra also generate the neural activity that underlies your thoughts and perceptions. The quantum mechanical interactions that power stellar furnaces also participate in the biochemical reactions that sustain life. Some interpretations suggest, though no scientific consensus exists on this point, that consciousness itself might represent another expression of the universe's fundamental unity across scales. The same principles of information processing and pattern recognition that operate in quantum systems might also manifest in the neural networks that create subjective experience and awareness. In the vast cathedral of cosmic space, JADES GSZ14-0 occupies a position that reveals something profound about the nature of existence itself. This galaxy formed in a universe that was not only younger but also significantly smaller and denser than the cosmos we inhabit today. The space between galaxies has expanded dramatically since the light we observe first began its journey, stretching the very fabric of reality and carrying distant structures beyond the reach of future observation. This cosmic expansion operates according to principles that challenge our everyday understanding of space and motion. Galaxies aren't flying through a pre-existing void like ships crossing an ocean. Instead, space itself grows between them, creating additional distance without requiring the galaxies to move through their local environments. It's as if the ocean itself were expanding, carrying ships farther apart without requiring them to sail. The implications for our understanding of existence are profound. If space itself can expand, then the arena within which all events occur is not fixed and unchanging. The stage upon which the cosmic drama unfolds is itself a dynamic participant in the story. This means that the context within which consciousness emerges and operates is fundamentally fluid and evolutionary. Consider how this cosmic expansion might resonate with your own experience of personal growth and development. The context within which your thoughts and experiences occur is not static. Your neural networks constantly rewire themselves based on new experiences. Your understanding of yourself and reality continue to expand throughout your lifetime. In a sense, the space of consciousness itself grows and evolves, creating new possibilities for awareness and understanding. The accelerating expansion driven by dark energy adds another layer of mystery to this cosmic cathedral. The universe isn't just growing, it's growing faster and faster with each passing moment. This acceleration began relatively recently in cosmic history, when the universe was roughly half its current age. Before that, the expansion was actually slowing down due to the gravitational attraction of matter and radiation. This transition from deceleration to acceleration represents one of the most significant phase changes in cosmic history. It suggests that the universe has entered a new epoch of evolution, one dominated by the mysterious properties of dark energy rather than the familiar influences of matter and radiation. We are living through a fundamental transformation in the nature of cosmic expansion itself. Every photon reaching us from JD's GS Z14-0 represents an archaeological artifact from the cosmic past, carrying within its electromagnetic structure precise information about the physical conditions that existed when it was first emitted. This ancient light has survived a journey spanning more than 13 billion years, maintaining its coherence and information content across distances that challenge human comprehension. The archaeological richness of this primordial radiation extends far beyond simple measurements of brightness and colour. Sophisticated spectroscopic analysis reveals the signatures of specific elements, the temperatures of stellar atmospheres, the velocities of gas clouds, and even the strength of magnetic fields in this distant galaxy. Each wavelength of light tells a different part of the story about conditions in the early universe. The presence of heavy elements in the spectrum of JD's GS Z14-0 provides particularly compelling evidence for the rapid pace of stellar evolution in early cosmic epochs. Elements like carbon, nitrogen, and oxygen were created in the nuclear furnaces of massive stars and distributed through space by supernova explosions. The detection of these elements in such an early galaxy means that multiple cycles of stellar birth and death had already occurred when the universe was less than 300 million years old. This stellar archaeology reveals a universe that was far more chemically mature at early epochs than our theoretical models had predicted. The efficiency of early stellar nucleosynthesis and chemical mixing must have been remarkably high to produce the elemental abundances we observe in galaxies like JD's GS Z14-0. This challenges our understanding of how quickly complex chemistry can emerge from primordial simplicity. As you reflect on this cosmic archaeology, notice how it mirrors the way your own memories preserve information about past experiences across the span of your lifetime. The neural patterns that encode your earliest memories have persisted through countless cycles of cellular renewal and molecular replacement. Like ancient starlight, these patterns maintain their coherence and information content across time, allowing the past to inform present experience. The isotopic ratios detected in early galaxies also provide clues about the nuclear processes that operated in the first generation of stars. These primordial suns were fundamentally different from contemporary stars, burning pure hydrogen and helium in nuclear furnaces that operated under conditions never again replicated in cosmic history. The isotopic signatures they left behind serve as fossils of stellar processes that occurred only once in the universe's evolution. The rapid growth of JDES GSZ 14-0 to such massive proportions in the early universe required a delicate balance between competing physical processes that astronomers call cosmic feedback. Star formation injects energy into galactic environments through stellar winds and supernova explosions, potentially halting further stellar birth by heating and dispersing the gas needed to form new stars. Yet somehow, early galaxies managed to continue growing despite these regulatory mechanisms. This cosmic feedback operates like a vast symphony where multiple instruments must play in harmony to create beautiful music. Gravity pulls matter together, attempting to concentrate gas and dust into stellar nurseries. Stellar feedback pushes back, trying to regulate the pace of star formation and prevent runaway collapse. The interplay between these competing forces determines how quickly galaxies can grow and how massive they can become. In the early universe, this symphonic balance appears to have been tuned differently than what we observe today. Perhaps stellar feedback was less efficient, allowing gas to cool and condense more readily into new generations of stars. Or maybe the gravitational wells created by dark matter halos were deeper and more concentrated, providing stronger forces to overcome stellar regulation. Take a breath and consider how this cosmic symphony might reflect patterns of balance and regulation in your own life and development. Growth and constraint, expansion and limitation, creation and destruction all participate in the ongoing dance of becoming. The same principles that govern galactic evolution might also operate in the development of consciousness, creativity, and personal transformation. The magnetic fields threading through early galaxies also played a crucial role in this cosmic symphony. These invisible structures helped channel gas flows, regulate star formation, and transfer energy across vast distances within galactic environments. The strength and configuration of primordial magnetic fields may have been key factors in determining how quickly early galaxies could assemble mass and achieve the impressive sizes we observe. Some theoretical models suggest that cosmic feedback processes were fundamentally different in the early universe due to the absence of heavy elements and dust grains. Without these materials to facilitate efficient cooling, gas clouds may have remained hotter and more turbulent, leading to different patterns of stellar birth and galactic assembly. This remains an active area of research rather than settled science. In the light from JDES GSZ 14-0, we encounter something that functions as a cosmic mirror, reflecting not only the physical conditions of the early universe, but also deeper questions about the nature of time, causality, and emergence. This ancient galaxy challenges our linear understanding of cosmic development, suggesting that the universe's capacity for creating complex, beautiful structures emerged much earlier than we had imagined. The mirror metaphor extends beyond poetic language to touch on fundamental questions in physics and philosophy. When we observe this distant galaxy, we're seeing it as it was, not as it is. The light reaching us today left JD's GSZ 14-0 when the universe was less than 300 million years old, but the galaxy itself has continued evolving for billions of years since then. We're looking into a cosmic past that no longer exists in the form we observe. This temporal displacement raises profound questions about the relationship between observation and reality. In quantum mechanics, the act of observation plays a crucial role in determining the properties of quantum systems, though this remains a subject of ongoing debate among physicists. While the measurement problem in quantum mechanics doesn't directly apply to macroscopic objects like galaxies, the parallel invites contemplation about the role of consciousness in cosmic evolution. Consider how this cosmic mirror might reflect aspects of your own existence and development. How much of your sense of self is based on memories of who you were rather than direct awareness of who you are in this present moment? The light from distant galaxies preserves images of cosmic conditions that no longer exist, much like memory preserves experiences from your personal past that continue to influence present awareness. The discovery that massive, complex galaxies existed much earlier than expected also mirrors patterns of emergence that we observe throughout nature. Complex systems often appear suddenly and dramatically rather than through gradual accumulation of simple components. Consciousness itself may have emerged in similar fashion, representing a quantum leap in the universe's capacity for self-awareness rather than a slow, incremental development. This cosmic mirror also reflects the interconnected nature of existence across vast scales of space and time. The elements that compose your body were forged in stellar furnaces billions of years ago and scattered through space by supernova explosions. The light that illuminates your daily experience originates in nuclear reactions occurring 93 million miles away in the sun's core. You are intimately connected to cosmic processes that span the entire history of the universe. As we delve deeper into the mystery of JD's GSZ 14-0, we encounter something that transcends the mere accumulation of astronomical data. The information encoded in the electromagnetic radiation from this ancient galaxy represents a form of cosmic language that bridges the gap between past and present, between distant stellar processes and immediate conscious awareness. This cosmic language operates according to principles that challenge our usual understanding of communication and information transfer. The photons carrying information from JD's GSZ 14-0 began their journey billions of years before Earth existed, yet they arrive precisely encoded with data about stellar temperatures, chemical abundances, and galactic dynamics. The information has been preserved with extraordinary fidelity across distances and timescales that dwarf human comprehension. The vocabulary of this cosmic language consists of electromagnetic frequencies, each carrying specific meaning about the physical processes that created it. Hydrogen atoms emit light at precisely defined wavelengths, regardless of whether they exist in terrestrial laboratories or distant galactic environments. This consistency allows us to decode the cosmic message with remarkable precision, translating patterns of light into understanding of stellar and galactic physics. But perhaps most remarkably, this ancient cosmic information interacts with the information processing systems in your brain to create conscious awareness of distant stellar phenomena. The electromagnetic patterns that encode data about early galactic evolution somehow interface with neural networks to produce the subjective experience of knowing about and contemplating cosmic history. Take a moment to appreciate the extraordinary nature of this information transfer. Patterns of electromagnetic radiation that began their journey when the universe was young now stimulate quantum processes in your visual cortex, creating thoughts and insights about cosmic evolution. You are not just receiving cosmic information, you are participating in a conversation that spans billions of years of space and time. Some interpretations suggest, though this remains highly speculative, that information itself might be more fundamental to reality than matter and energy. In this view, the universe could be understood as an information processing system where consciousness represents the most sophisticated expression of cosmic computation. This idea remains unproven and controversial, but it offers an intriguing perspective on the relationship between mind and cosmos. As our contemplative journey through cosmic deep time approaches its natural rhythm, we find ourselves not at a destination, but at a threshold, a doorway into even deeper mysteries that stretch infinitely beyond the boundaries of current understanding. The discovery of JD's GS-Z14-0 represents just one note in a cosmic symphony that has been playing for billions of years and will continue long after our sun exhausts its nuclear fuel. This threshold invites us to embrace a particular kind of intellectual humility, a recognition that the universe consistently exceeds our expectations and challenges our theoretical frameworks. Each new discovery reveals how much we still don't understand about the fundamental processes that govern reality at every scale. The cosmic mystery deepens rather than diminishes as our observational capabilities expand. The James Webb Space Telescope has been operational for only a few years, yet it has already revolutionized our understanding of early cosmic evolution. Future instruments will peer even deeper into space and time, potentially detecting the very first stars to ignite in the cosmic dark. Each new observation will expand our knowledge, while simultaneously revealing new questions that await investigation. But perhaps the most profound mystery involves consciousness itself and its relationship to the cosmic processes we've been exploring. The same universe that created massive galaxies in its youth also created the neural networks that allow you to contemplate cosmic evolution. Through consciousness, the cosmos achieves a form of self-recognition that represents its most remarkable evolutionary achievement. As you sit at this threshold between the known and unknown, notice how the cosmic mysteries we've explored reflect the ongoing mystery of your own existence. How do electrochemical processes in neural networks give rise to the subjective experience of awareness? How does matter organized in the specific patterns of your brain become capable of contemplating infinity? These questions remain as mysterious as the rapid formation of early galaxies. The threshold we occupy also represents a unique moment in cosmic history. We exist during an epoch when the cosmic microwave background radiation is still detectable, when distant galaxies remain visible, when the evidence for cosmic evolution can still be observed and studied. Future civilizations may not be so fortunate as dark energy accelerates cosmic expansion and carries distant structures beyond observational reach. In these final moments of our cosmic meditation, we return to something that has been present throughout our journey, but perhaps hasn't been fully appreciated until now. The light from JD's GS-Z14-0 connects us directly to processes of cosmic becoming that have been unfolding for billions of years and continue in this very moment of awareness. The galaxy we've been contemplating no longer exists in the form we observe. It has continued evolving for over 13 billion years since the light we detect first began its journey. It may have merged with other galaxies, exhausted its star-forming gas, or developed into something completely different from what we see through the Webb telescope. We're observing a moment frozen in cosmic time, a single frame from a movie that has continued playing long after that scene concluded. Yet in another sense, JD's GS-Z14-0 exists eternally in the light that continues to reach us across the cosmic dark. Each photon carries within itself a perfect preservation of the conditions that existed when it was first emitted. The ancient galaxy lives on in the electromagnetic radiation that bears witness to its early existence, creating a form of cosmic immortality through light itself. This eternal preservation through light offers a profound metaphor for the nature of existence and memory. Your own experiences become preserved in the neural patterns that encode them, allowing past moments to influence present awareness across the span of your lifetime. Like ancient starlight, these patterns maintain their coherence and meaning across time, creating continuity between past and present experience. The dance of cosmic becoming continues through your consciousness in this moment. The same creative forces that assembled the first galaxies in cosmic dawn operate through the emergence of thoughts, insights, and moments of wonder in aware beings throughout the universe. You are not separate from cosmic evolution. You are one of its most remarkable expressions. As you breathe in this recognition, allow yourself to feel the profound privilege of existing at a moment when such cosmic connections can be perceived and appreciated. Throughout most of the universe's history, no conscious observers existed to contemplate cosmic evolution. The emergence of awareness represents a phase transition in cosmic development as significant as the formation of the first stars or galaxies. The same mystery that allowed massive galaxies to form impossibly quickly in the early universe also allows moments of recognition and wonder to emerge in consciousness. The universe that surprised us with its rapid early creativity continues to surprise us through the ongoing emergence of awareness, understanding, and appreciation for cosmic beauty. You are both witness to and participant in this eternal dance of becoming. The ancient light continues to whisper its cosmic secrets, reminding us that existence itself is far more mysterious and beautiful than our theories can fully capture. The impossible galaxy that challenges our understanding of cosmic evolution also challenges us to remain open to the ongoing mystery of consciousness and its place in the cosmic story. In the gentle recognition that you are made of processed starlight, organized into patterns complex enough to contemplate the stars that created you, we complete one movement in the cosmic symphony while preparing for countless others yet to unfold. The journey into cosmic mystery continues with each moment of conscious awareness, each scientific observation, and each insight that bridges the gap between the vast scales of cosmic evolution and the intimate experience of existing as a conscious being in an infinite universe. In the gentle stillness that follows our cosmic meditation, something extraordinary begins to unfold within the space of awareness itself. The same capacity for wonder that allows you to contemplate ancient galaxies continues to operate in ways that transcend the specific content of any single discovery. This faculty of wonder, this ability to be moved by mystery, represents something as remarkable as the cosmic phenomena we've been exploring. Consider for a moment the neural architecture that makes cosmic contemplation possible. The electrochemical patterns flowing through your brain at this very moment are creating the subjective experience of understanding concepts that extend far beyond the immediate sensory environment. Your consciousness can hold ideas about galaxies that formed billions of years before Earth existed, about quantum processes occurring at scales smaller than atoms, about mathematical relationships that govern the behavior of matter across the entire observable universe. This cognitive capacity didn't emerge in isolation. It developed through billions of years of biological evolution, shaped by natural selection, acting on organisms that needed to navigate complex environments and make survival decisions based on incomplete information. Yet somehow, this survival-oriented cognitive apparatus also possesses the ability to appreciate beauty, to feel awe at cosmic vistas, and to derive satisfaction from understanding abstract mathematical relationships. The same neural networks that evolved to recognize patterns in immediate environments now allow you to perceive patterns that span cosmic history. The brain regions that develop to navigate social relationships now contribute to your ability to feel connected to the vast community of conscious beings scattered throughout space and time. This represents a remarkable expansion of cognitive function beyond its original evolutionary purposes. Take a breath and notice how this recognition of cognitive wonder might relate to your ongoing experience of curiosity and discovery. The questions that arise naturally in your mind about cosmic mysteries reflect the same exploratory impulse that drives scientific investigation. You participate directly in the process of cosmic self-discovery through your capacity for wonder and inquiry. Some interpretations suggest, though this remains a speculative idea rather than proven science, that consciousness itself might represent the universe's method for achieving self-awareness. Through the emergence of conscious beings capable of cosmic contemplation, the cosmos develops the ability to recognize its own beauty, complexity, and creative potential. This perspective, while unproven, offers a poetic framework for understanding the relationship between mind and universe. As we prepare to complete this particular journey through cosmic mystery, we encounter something that reveals the recursive nature of understanding itself. Each insight about the universe simultaneously deepens our appreciation for the mystery of consciousness that makes such insights possible. The more we learn about cosmic evolution, the more remarkable it becomes that matter can organize itself into patterns capable of comprehending cosmic evolution. This recursion operates at multiple levels of analysis. The atoms that compose your brain were forged in stellar furnaces similar to those that illuminated Jades GSZ 14-0 billions of years ago. The nuclear processes that created the carbon, nitrogen, and oxygen in your neural tissue followed the same physical laws that governed stellar nucleosynthesis in the early universe. The electromagnetic forces that enable neural communication operate according to principles that also determine how light travels across cosmic distances. Yet somehow, when these stellar materials become organized in the specific patterns of a functioning brain, they give rise to subjective experience, to the felt sense of being aware, to the capacity for wonder and understanding that has guided our entire exploration. This emergence of consciousness from cosmic matter represents one of the most profound phase transitions in the history of the universe. The mathematical precision required for this emergence is breathtaking to contemplate. The fundamental constants of physics had to take exactly the values they do for stars to form, for heavy elements to be created, for planets to develop, and for the complex chemistry of life to become possible. Any significant variation in these constants would have resulted in a universe incapable of supporting the emergence of conscious beings. This apparent fine-tuning of cosmic parameters has generated extensive debate among physicists and philosophers. Some interpretations suggest the existence of multiple universes with different physical constants, making our life-supporting universe just one possibility among countless others. Other perspectives propose that consciousness itself might play a fundamental role in determining the structure of physical reality, though this remains highly speculative and lacks scientific consensus. As we reach the end of this cosmic journey through deep time, we find ourselves transformed not by definitive answers, but by profound questions that will continue to illuminate our understanding long after tonight's exploration concludes. The impossible galaxy JADES GS-Z140 stands as more than an astronomical anomaly. It represents a gentle reminder that the universe holds mysteries far grander than our current theories can embrace, and that our role as conscious observers places us at the very heart of an unfolding cosmic story that began with quantum whispers and continues through each moment of aware recognition. The same creative forces that assembled massive structures in the universe's youth continue to work through your capacity for wonder, ensuring that the journey into cosmic mystery will never truly end. If you found yourself moved by tonight's exploration of how impossible structures emerge from the quantum foundations of reality, you might discover fascinating connections in another journey we can take together. The same fundamental forces that shaped massive galaxies in the universe's youth continue to influence your daily existence through mechanisms that most people never recognize. These hidden connections between cosmic evolution and personal transformation await your discovery in They've Hidden This Energy, Secret Your Entire Life, where we'll uncover how the deepest principles of physics manifest in the most intimate aspects of human experience. Until we meet again in the vast cathedral of cosmic mystery, may you carry with you the recognition that you are both witness to and participant in the universe's ongoing story of impossible beauty emerging from apparent emptiness. The ancient light of distant galaxies illuminates not just the cosmic past, but the eternal mystery of consciousness itself awakening to its own cosmic nature. Of consciousness itself awakening to its own cosmic nature.